Hello students, welcome back. Now we are going to discuss about packing efficiency. Let us say suppose I have given you some spheres and I asked you to fill these spheres efficiently in a given volume. So the one who left with the minimum empty space is the one who arranged them efficiently. So which is the most efficient structure we have in the solid state? So let's learn more about it. So let's start. So now we are going to learn about packing efficiency. It is also known as packing fraction. So what is packing efficiency or packing fraction? Let's discuss about it. It is the percentage of total space filled by the particles. We know that solid is made by particles. The particles may be atoms, maybe ions, maybe molecules. So the particles are going to occupy the space. So it is a percentage of the total space occupied by the particles, right? So if I consider a cube and it is filled by some particles, so the packing efficiency is how efficiently they are packed. So if they are packed closely, then packing efficiency will be high. If they are packed loosely, then their packing efficiency is going to be less. So a close packed structures are going to have more packing efficiency or more packing fraction, right? So basically we want to minimize the voids. We want to minimize the void space. So we require close packed structures in which the space is efficiently occupied. Okay. So it is the total percentage of the total space filled by the particles. So here the particles that we are going to consider are hard spheres, right? The rigid spheres, where you can see in this picture where there are two types of particles which are closely packed, so as to minimize the what I can say empty space between the particles. Okay. So mathematically the packing efficiency is defined as the volume occupied by the particles, the volume occupied by the all spheres or all particles in unit cell divided by the total volume of the unit cell. So here we require two quantities to know. One is the total volume of the unit cell and other is the volume occupied by all the particles present inside the unit cell. Okay, so mathematically you can calculate the packing efficiency from this formula. So generally the efficiencies of common structures, if you consider the simple cubic has 52.4%. That means out of 100%, only 52.4% is occupied by the particles. That means roughly 50% is occupied by the particles and remaining 50% is just vacant. Okay, so only around 50% is occupied and the remaining 50% is wastage space. So next is BCC, which is a bit more close packed structure as compared to simple cubic, in which 68% is occupied. So remaining 32% is the void space, and next highest is the face centered cubic, which is hexagonal close packed or cubical close packed. So these two structures are having 74% of packing efficiency, which is the highest. 74% of the space is occupied and the remaining 26% is vacant space. So here this is having the least efficiency, packing efficiency, and this is having the FCC, HCP are having the highest packing efficiency. Okay, so let's calculate how these numbers came. Let's calculate the packing efficiency of simple cubic, 52.4%, and also calculate the packing efficiency of all the other two structures as well. So first we'll start with the simple cubic structure. First we'll calculate the packing efficiency of simple cubic structure. Okay, so here this is the arrangement of the particles in simple cubic or a primitive cubic unit cell, in which the particles are occupying the corners of the unit cell. Let us suppose that the unit cell, its edge length is A. So A is the edge length of the unit cell and R is the radius of the sphere, that is the radius of the particle. Okay. In case of the simple cubic unit cell, the particles touch along the edges. Okay. So this is the center of one particle and this is the center of the surrounding particle. So they are touching along the edge length. So this distance is actually A, that is the edge length A equals to 2 times radius. This is the R and this is R. Since all the particles are identical, so 2R is equals to A. So A is equals to 2R, which is the radius relation between the edge length and radius of the particle, which is very, very important if you want to calculate the packing efficiency. Okay. So we discussed that packing efficiency is the volume occupied by the particles in the unit cell divided by the volume of the unit cell. Okay. So here the unit cell is a cube. So we know that the volume of the cube is what? A cube, where A is the edge length. So here A is equals to 2R. So 2R cube, that is 8R cube is the volume of the unit cell as a whole. But let's calculate the volume occupied by the particles which are present inside the unit cell. We know that in case of a simple cubic unit cell, the particles are occupying only the corners. So we have 8 particles. Each particle contribution is 1 by 8. So 1 by 8 into 8 is equals to 1. So effectively only one sphere is belonging to the unit cell. Okay. So one sphere into volume occupied by that one sphere is equals to what? 4 by 3 pi r cube. So this is of the volume of one sphere into, we have only one particle, that is one sphere inside. So basically it is 1 into 4/3 pi r cube. So this is the volume of the sphere divided by 4/3 pi r cube divided by volume of the cube, that is 8r cube. So r cube will get cancelled. So if you calculate, the value comes around 0.524. So if you convert it into percentage, you have to multiply it by 100. So if you multiply it by 100, you will get 52.4%. So this is the packing fraction or packing efficiency of a simple cubic unit cell. Okay. So which is only 52.4% efficient, and the remaining percentage is the void percentage, right, which is empty space. So this is not a closed packed structure. Only 50% of the space is occupied and we are leaving the 50% of the space vacant. So this is not a good efficient way of filling the particles. Okay. So let's calculate the packing fraction of a next closed packed structure, that is body centered cubic structure, BCC. Okay. So we know that BCC unit cell packing fraction is 68%. So let's see how we got that 68% as the packing fraction. Okay, this is the unit cell of BCC. So in body centered cubic unit cell, you can see the spheres that touch along the body diagonal. This is one important point that you have to understand here. So if you know this thing, that how the particles are touching each other, then half of the question you can easily solve. So here this is one particle, this is one more particle, and this is one more particle. So 3 particles are touching along the body diagonal. Okay. So this is the body diagonal and 3 particles are touching. So as the sphere at the center touches the sphere at the corner, right? Sphere at the center touches the sphere at the corner. So here you can see this is radius r plus this is diameter 2r plus radius r. So total 4r is the length of the body diagonal. So 4r is equals to root 3a is, this is the body diagonal length if you express it in edge length. Okay. Root 3a is the body diagonal length that you can observe from here, right. So this is the body diagonal. So this is the edge length a and this is root 2a. So from Pythagoras theorem you can calculate this length, and that comes root 3a. So root 3a is equals to 4r and a equals to 4r by root 3. So this is the relation between the edge length a and radius of the particle. Okay. So we can use this relationship in calculating the packing fraction. So volume of the unit cell is a cube. So substitute a in terms of r. So you will get 64 r cube by 3 root 3, right. So this is the volume of the unit cell, and next thing is the volume occupied by the particles. Volume occupied by particles, to calculate we have to know how many number of particles are there in BCC unit cell. So in BCC unit cell we have 8 particles at corner. So 1 by 8 into 8, which is equals to 1, and we have 1 at body center. So total we have 2 particles, right? So 2 into volume occupied by each particle, that is 4/3 pi r cube. That is 4/3 pi r cube is volume occupied by one particle into there are 2 particles. So 2 into 4/3 pi r cube is the volume occupied by the 2 spheres in the unit cell divided by the total volume of the unit cell, which we already calculated. So this is just if you do the calculation, you will get 68% is the packing efficiency of a BCC, body centered cubic unit cell, which is more efficient than the simple cubic unit cell. Okay, so let's move to the packing fraction of FCC unit cell, which is the most efficient structure, most efficient unit cell, right? So here in this case we have less void percentage and we have more space. The given space is filled more efficiently in FCC or HCP unit cell. So let's calculate the packing fraction of this. So if you see in case of FCC, the particles will touch along the phase diagonal. So the particles are touching along the phase diagonal. So the particle at the center of the each phase will touch the corner particles. Okay. So here this is edge length A and this is edge length A. So from Pythagoras theorem, the AC, the phase diagonal AC length is equals to the 4 times the radius of each sphere. Alright. So AC is equals to 4R. So AC is equals to root 2A. So root 2A will become 4R. Root 2A will become equals to 4R. So this is the relationship between A and R. And in case of FCC, there are 4 spheres. So volume occupied by the 4 sphere is equals to this much. Yeah, this is 4R equal to root 2A. So A you will get equals to, that is A is equals to 4R by root 2 you will get. So volume of the cube is equals to, volume of the cube equals to what? A cube, that you will get. So if you calculate the packing fraction from the formula, you will get the value, that is 4 into 4/3 pi r cube is the volume occupied by the 4 spheres in the FCC unit cell divided by the volume of the unit cell as a whole. So if you solve it, you will get 74%. This is the out of 100%, 74% volume is occupied by the particles and remaining 26% is just the empty space. Okay. So from this thing, what we understand is we understand that FCC unit cell or HCP, even if you calculate for HCP, you will get the same 74%, the packing fraction. So HCP and FCC are close packed structure which are in which the space is used up efficiently, and the next is BCC unit cell, which is having 68% of packing efficiency, and the least efficiency is having the simple cubic unit cell is having the least packing efficiency. Okay. So this is all about the packing fraction. So let's do some questions based on the concept that we learned till now. So calculate the void fraction for the structure formed by A and B atoms such that A form HCP structure and B occupies 2/3 of octahedral voids. Assuming that B atoms exactly fitting into the octahedral voids in the HCP formed by A. Okay. So though the questions seems to be lengthy, but it is easy question, it is not a difficult question. So let's solve it. So here the structure is formed by A and B, and A is occupying the HCP and B occupies 2/3 of octahedral voids. So from this information you have to calculate the void fraction. Okay. So let's calculate the void fraction. Void fraction is what? Void fraction is the volume occupied, it is the volume occupied by the voids, that is the empty space we have to calculate. So to calculate the empty space, we have to calculate the packing factor or packing efficiency. Okay. So let's calculate that. So it is given that A atoms are occupying HCP. So we know that in HCP unit cell 6 particles will be there. The number of particles inside HCP is 6 particles into volume occupied by each particle of A is 4/3 pi RA cube, right. So this is the volume occupied by A particles. Similarly, B if you take, it is occupying 2/3 of octahedral voids. So we have to know how many octahedral voids are there in HCP. How many? In HCP we have 6 close packed spheres. So the number of close packed spheres is equal to number of octahedral voids. So there will be 6 octahedral voids. So only 2/3 of 6 octahedral voids are occupied. That means only 4 atoms of B is effectively present, and volume occupied by each particle of B is 4/3 pi RB cube. So this is volume occupied by A and then volume occupied by B. And next thing is, what we need to do is calculate here is, assuming that B atoms exactly fitting into octahedral voids. B atoms are exactly filling into the octahedral voids. So that is given in order to relate RA and RB. RA and RB, that is actually given. So here B atoms are exactly fitting into the octahedral voids found by A. That means RB by RA should be equals to 0.414. Okay. So radius of atom B is equals to 0.414 of radius of A, because atoms of B are occupying the octahedral voids found by A. So to fill in, the radius of B should be this much. Okay. So from here what you can write is 4 into 4 by 3 into pi into RB is what? 0.414 into RA whole cube. So this is the volume occupied by the particles of B, and this is the volume occupied by the particles of A is this much. Okay. So now we can calculate the total volume occupied by the particles, which is VA by VB divided by volume of the HCP unit cell as a whole. So if you recall, the volume of HCP unit cell is 24 root 2 R cube. Okay. So if you add these two, that is 6 into 4 by 3 into pi RA cube into plus it is 4 into 4 by 3 pi into 0.414 RA cube divided by, which is equals to 24 root 2 RA cube. So from this thing you can calculate the packing fraction. It is just simple calculation, and if you calculate that value, it comes around 0.7756 exactly. So this is the packing fraction, but you want void fraction. So void fraction can be calculated from packing fraction just by substituting, just by subtracting this value from 1. So 0.7756. So the value comes exactly 0.2244 is the void fraction of the unit cell. Okay. So this is the way to calculate the correct answer. Okay. So 0.2244 will be the answer. Now let's see the second question based upon the same concept. The packing efficiency of the two-dimensional square unit cell shown is. It was a question given in JEE 2010. So here a two-dimensional square unit cell is given. It's a two-dimensional square unit cell in the particles. One particle is at the center and 4 other particles are at the corners. So we have to calculate the packing efficiency of this 2D square unit cell. Okay. So here in 3D, volume of the particles by volume of the unit cell. In 2D, area, right? Area comes into picture. So the volume of the unit cell is nothing but the volume is equals to area occupied by the particles inside divided by area of the square unit cell as a whole. So here, what is this area? This is its side length is equals to L. So area of the square is nothing but L square. So area of the unit cell we got easily, it is L square, and area of the particles which are present inside. So here this is one particle and there is 1/4. So total this is 1 by 4th, 1 by 4th, 1 by 4th, 1 by 4th. So if you add these 4, you will get 1 plus 1, 2, right? 2 circles are actually belonging to this square, right? So 2 into each one is having area pi r square. Okay, so here we need to find a relationship between r and l. So r and l, the relationship is what? This is r plus 2r plus r, 4r. This diagonal 4r is equals to root 2l, right? Root 2l is equals to 4r. So what we'll get? L is equals to 4r by root 2. So it is 2 root 2r. 2 root 2r. So L is equals to 2 root 2r. So simply put the value here, 2 pi r square divided by 2 root 2r is nothing but 2 square 4, 4 to 8, 8 r square. So r square will cancel and you will get 2 pi by 8, that's equal to pi by 4. Pi by 4 into 100%. So it is 25 pi. So 25 pi, how much value? Pi is 3.14. So it will be 78.54 is the packing efficiency of this 2D square unit cell. Okay. So here the question is, it is a 2D problem. So in 2D problem, we don't have, instead of volume, we have to take the area. So area belonging to the square divided by area of the cell as a whole, that is area of the square, area of the square. So you will get 78%. That means these particles which are present inside are occupying the 78.54% and the remaining around 22% is this void space. This one, this is a void space, this is a void space, this one around 22%. Okay. So this is the way to solve the questions on packing efficiency. So students, in this part we discussed about the concept of packing efficiency or packing factor. We calculated the packing efficiencies of some common unit cells, like we calculated for simple cubic, body centered cubic structure and face centered cubic structure as well. So we got to know that the face centered cubic structure is the most efficient crystal structure we have. So in our next part, we are going to discuss about the structure of some common ionic compounds. So keep watching for my next part.